Hi, my name is Sean Zong, and this is my Physics 22 lab report, Lab 2, Charge Tape Revisited. So, before we get into the presentation, I'll just go over the contents of what we'll be going through in this video. So, firstly, the introduction, where I'll discuss the purpose and fundamentals of this lab. Secondly, the procedure, where I'll talk about the setup and results. Third, the code, where I'll go over the computational models that I generated. And then fourth, the questions of what if and why further explored. So the purpose of this experiment is to compare the charges between the point charge model used in Lab 1 to a line charge simulation model in GlowScript that effectively models many back-to-back point charges instead. So as a bit of a spoiler, from Lab 1, we assigned a charge value of 1.335 times 10 to the negative 8th coulombs for the point charge. And then for Lab 2, we find that each point, for the line charge, the charge is 2.685 times 10 to the negative 8th coulombs. So the fundamental principles that guide this lab are first off Newton's second law, which is that F net is equal to the change in momentum over change in time. It also states that the net force is equal to the sum of each of the individual forces, which in this case is the gravitational force and electric force, both of which being equal in magnitude but opposite in direction. So the gravitational force here is modeled by negative mg in the y component, with g being, of course, 9.81 meters per second squared, and the electric force being displayed here to the right. So for the computational setup, I edited a glow script with initial charge guesses, constants, experiment parameters, gravitational force, and definitions of electric force and electric field. Secondly, I iteratively changed the number of point charges used to approximate the line charge until the electric force converged. After that, I iteratively changed the guess charge until the electric force from the line charge was equal to the gravitational force. And then finally, I scaled the arrows in the model so that it would properly represent the forces and fields. So for some of the parameters used in the model, we repeated a lot of the stuff from Lab 1, where the system is tape B, the top tape, the surroundings being tape A and Earth, tape A being the bottom tape that exerts a force on the top tape. So tape A and B are both 0.2 meters long, and we're given that 1 meter of tape is about 1 gram of mass. So tape A and B masses are both about 0.2 grams. And then the distance between the top and bottom tape at which the gravitational force is completely canceled out by the electric force is 2.86 centimeters. So for the calculations, we make some key assumptions that the charges are still equal in this case for the top tape and bottom tape. We also negate air resistance as well in our force balances. But this is the same as part 1, where overall the electric force is just going to completely balance out the gravitational force and be 0.00196 newtons in this case. So for the code, this first section right here, I plugged in the constants. That value for Q was iteratively determined after a number of steps down the line. This is my function for determining the electric fields, pretty standard. And then here I had to put in 350 point charges before the electric force value converged. So that is what I'm just trying to show here. And then here, these last two boxes are just showing the scales that I use to try and demonstrate those forces and fields in the model. And this last block of code right here, I just replaced a number of the non-initialized vector components with the actual formulas so that the code would run and calculate the correct magnitudes, but that's really all there is to this part. So here's the actual computational model. As you can see, the bottom tape, tape A, is represented by the blue charges, and tape B represented by the red charges up top. The white arrow represents electric force, yellow arrow represents gravitational force, and then those green arrows represent the electric field. As you can see, our magnitude of electric force is essentially equal to our gravitational force, so that shows that the charge that we chose was correct. Potential sources of error, we might have lost charge, and there was also probably uneven charge because we handled the tape strips to be situated one another, and there was certainly charge transferred to the surroundings, so that assumption of the tapes having equal charges is likely not a good assumption. Frictional losses, we did neglect air resistance altogether, and the movement of the tape is definitely affected by the air's viscosity. And also we assumed a uniformly distributed charge, and that just means that we assumed that across the point charges on each tape that they were spread evenly across the length. So for the further questions, what if you had modeled each of your tapes as a single point charge like in the previous lab? Well, here are the values for the charges, and as we can see, the charge on each tape increases significantly in the line charge model to produce the same electric force as in lab 1. If approximating as a point charge, the magnitude of charge can be smaller. And why do these estimates differ, and which one is likely closer to the real value? The charges are spread horizontally across the tape strip, so the interacting charges are further apart. The effective force from each charge interaction is weaker. The line charge model is likely to be more close to the real value since it accounts for the increased charge distances.